Hi, this is Terry Kuzma here at Penn State University. We're taking a look at lectures in bottom-up manufacturing, and what we're going to look at today is carbon allotropes, processes, and applications, and this is part 2 in our series. So in our history, what we did before previously, we looked at an overview of carbon, and then initially we took a brief overview of diamond-like coatings. And so now that took place in 1953, so moving up the history timeline in the, I guess, the accepted credit for different carbon allotropes, we're going to move up to the 1980s when buckyballs were first highly researched and credited. So what we're going to do, like we did in the previous uh, presentation and all the presentations, we're going to take a look at the discovery, some material properties and physics, the manufacturing methods, and then some applications. So the fullerene discovery, it was discovered, or the credit was given in 1985 to Smalley, Croto, and Curl at Rice University. And then in 1990, they actually were able to synthesize larger quantities of this material, and they were awarded the Nobel Prize in 1996. So this shows a picture of these people over on the side. So it shows Smalley on the left, Curl, and then Croto and Heath in this picture. Oh, I'm sorry. It's starting left to right is Sean O'Brien, and then it moves to the left. So discovered, fullerenes were discovered and documented in 85 by Croto. A fullerene is a molecule of carbon that may include many shapes. The molecule is based solely on carbon and might be a sphere, a tube, ellipsoid, or a combination of these shapes. Historically, the fullerene was the first widely studied synthetic carbon allotrope, and the buckyball is a special subset of the fullerene family. The buckyball, or the quintessential buckyball, are comprised of 60 covalently bonded carbon atoms. So this is characteristic of a soccer ball shape. It's a self-assembling structure. It was discovered in 85 by Smalley, Croto, and Curl at Rice University, and again in 1996 they were awarded the Nobel Prize in chemistry. So it was named after Richard Buckminster Fuller, who was an architectural designer that popularized the geodesic dome system. And there's houses here in Pennsylvania. Locally to me, there's a couple, I guess they're rather rare, that are made on that geodesic dome. They're actually out in the country. Sometimes this is called the third allotrope of carbon, the fullerene. So let's take a look at material properties and physics. So the physics and geometry, we can see the assembly here that we have 60 atoms, hexons, that cannot form a sphere. So we would look at how these things were formed in energy and how the ring reactant gives us this particular shape. So this is a visualization of the different constituents that are involved in here. So we can overlay these different geometric shapes to take a look at the formation of the buckyball. So again, this shows us the buckyball configuration, how it's similar to the soccer ball. And interestingly, here in the lower right-hand corner, we can see that often people propose for both buckyballs and carbon nanotubes that we're able to encapsulate different material within that particular system. So often these could be materials such as hydrogen. So these could be used as a hydrogen fuel cell type storage system. So the C60 fullerene, also known as the buckyball, it's a 32-sided structure comprising of 12 pentagons and 20 hexagons. Each carbon atom in the C60 is trigonally bonded to other carbon atoms. There are 20 hexagonal faces and 12 additional pentagon faces in each C60 molecule. The C60 molecule has 2 bond lengths. There's a 6-to-6 ratio bond rings between the 2 hexagons, and these can consider double bonds, and they're shorter than the 6-to-5 bonds that are between the hexagon and the pentagon. The average bond length here is 1.4 angstroms, and this is the same bond length as graphite. The nucleus-to-nucleus diameter of C60 is about 0.71 nanometers, and the C60 molecule is about 1.1 nanometers in diameter. So the C60 nucleus to nucleus is about, like we said, 0.71 nanometer. And then if we look at a pure, or almost pure solution of these fullerenes in a solution, they often give off a deep purple color. So that's shown in this test tube right here. So there's other fullerenes that we can get from this basic structure that include different amounts of pentagons and hexagons. So the fullerenes are formed geometrically by adding hexagonal faces. Euler's theorem states that closed surfaces consisting of hexagon and pentagons have exactly 12 pentagons and an arbitrary number of hexagons. So we can look at these different shapes that are common and then the nomenclature for them here on the right-hand side. So again, these are the selected allotropes that we looked at previously, and the ones that we're focusing on are D, E, and F. So that shows these are our fullerene derivatives. So fullerenes are similar in structure to graphite, which is composed of stacked graphene sheets of linked hexagonal rings. Fullerenes are found in nature and have been detected in outer space. So again, fullerenes come in many different formats, and these are made in nature all the time, and they're hidden in soot formed by lightning discharges from the atmosphere and just cooking in candles, etc. So they're certainly can be man-made, but they're made in nature also. So fullerene properties, they have high electrical conductivity due to free electron on every carbon atom. It becomes a superconductive when doped with potassium at minus 255 degrees C. It's a metallic conductor at room temperature and three-dimensional conductor that conducts equally well in all directions. And it may become an ideal material for making superconducting wires. So other fullerene properties that can withstand very high temperatures and pressures. It has the ability to trap other molecules in its cage structure. It exhibits ferromagnetic properties. It has thermal conductivity as good as those of diamonds. It's twice as hard as diamond when compressed to 70% of its original size. And it has black body radiation property. It absorbs and reemits all radiation landing on it. So other fullerene properties, it has thermal conductivity as good as those of diamonds. It's twice as hard as diamonds when compressed to 70%. That was in the last slide. It has black body radiation. Again, that was in that last slide. So chemically, fullerenes are soluble in many organic solvents. The functionalization can further control and enhance the solubility. Fullerenes and organic solvents exhibit 5 stages of reversible oxidation or reduction. Redoxidation is short for reduction-oxidation reaction, is a chemical reaction in which the oxidation states of the atoms are changed. So oxidation is the loss of electrons or an increase in oxidation state by a molecule, atom, or ion. And reduction is the gain of an electron or decrease in oxidation state by a molecule, atom, or ion. So this is the properties of the materials here. We can take a look at these symmetrical peaks of absorption for the different sizes of carbon fullerenes. So let's take a brief look at manufacturing, common manufacturing methods. We can have, this is the manufacturing method that they use to win the Nobel Prize at Rice University. So what they do is they use a inert environment pumped down to 100 millitorr, and basically what they did is they did a laser ablation to a rotating graphite disc, and they were able to form these carbon derivatives and collect them and be able to filter them on the surface. So again, the size and constituents of this particular type of process is controlled by the laser energy, the angle of the laser on the surface, and the rotation speed of the graphite disc. So fullerenes are generated by the vaporization of pure graphite at a pressure of around 500 torr. Excuse me. Vaporized graphite collects as soot on the graphite cathode. Carbon atoms begin to self-assemble, forming a C6 molecule, and fullerenes removed from the carbon soot using AFM and specialized technique are used to sort the different types of configurations. So this is first used in the 90s, and probably one of the first methods that became really popular for carbon arc discharge methods. A problem with this per se, or an association with this process, is we not only get fullerenes, but we would get carbon nanotubes, we get all kind of different derivatives in between. So what we basically do is try to control the process as much to get a tight Gaussian distribution as possible with the particular derivative that we are looking to manufacture. So this discharge can contain up to 50% of fullerenes, and with C60 at 13% and C70 at about 2%. So again, this is a lowdown on, and I don't have the schematic picture from that book, but this is a lowdown on that distribution that I was referring you to from before. And what we can do is we can use chromatography to separate the different materials that are made in this configuration so that we can get a more pure concentration of a particular fullerene. So we would use solvents such as toluene, which we all understand is carcinogenic, and that's an added cost to this in different ways to this particular process. And it's also very low yield, and this takes a lot of labor. So this is, I guess, troublesome or expensive to make in this particular configuration. So this shows the different types of synthesis that we could use. These are the percentage here, and these are the ratio of different materials and the separation systems that we would use for these particular manufacturing methods. So particular applications of fullerenes, we can look at medical applications. So we can look at caged medicines, etc., for these uses of these materials. And we can also look at coatings that we would use these for, like scanning tunneling microscope tips. We can also use these materials as lubricants, and then we could use these as heterojunctions in solar cells. So I'd like to end this presentation on buckyballs right there. So the next time what we're going to do is move on our timeline, and we're going to take a look at multi-wall carbon nanotubes. Thanks for your attention, and we'll see you next time.